12.1. Define and use sequences and series. Vocabulary. What's a sequence? A sequence is a function whose domain is a set of consecutive integers. It's a big fancy way to say that a group of numbers, a list, like 1, 3, 5, 7. Now, these are actually the terms of the sequence, which is the range. The domain would be the first number is 1, the second number is 3, the third number is 5, and the fourth number is 7. And so this would be a sequence. A series is a expression that results when the terms of a sequence are added together. Okay, summation notation. It's a notation that represents the sum of the terms in sigma notation is another way to say that, and we use this Greek letter sigma to show that we're going to add these terms together. So let's talk about this more. A sequence. A sequence is a function whose domain is a set of consecutive integers. If a domain is not specified, it's understood that the domain starts with 1. The values in the range are called the terms of the sequence. The relative position of each term is the domain. Like the first number is A1. The A stands for what the value of the first term is. And then we usually say this 1 here is an n. So when we say A to the n, we mean what's the value for the nth term in this nth position. So if we're looking for the third odd number, we'd say A, the third position is 1, 3, 5. Okay. And finite sequence has a limited number of terms, stops. An infinite sequence continues going on forever, and we use these 3 dots to show that. A sequence can be specified by a rule. For example, both sequences above can be described by a to the n, or an, sorry, not to the, because that would mean exponential. So an would be, you take whatever the n is, the position number, and multiply by 2. So if I want the third position of that, I'd say a to the third equals 2 times n, which is 3, or 6. Okay, so we're going to write the terms of a sequence. Example 1. Here's our sequence rule. We want the value in the nth position, and we get that value by taking 2 to the n plus 1 exponent. So the value in the first position would be 2 to the 1 plus 1, or 2 squared. That would be 4. Second position would be 2 to the 2 plus 1, or 2 cubed, which is 8. Third would be 2 to the 3 plus 1, which is 2 to the 4th, 16. And you can get the rest of it from there, can't you? Okay, example 2. Write the rules for the sequences. Describe the pattern and write the next term. Write a rule for the nth term of the sequence. Okay. Before we start these, it's helpful to go ahead and write the domain. So let's list the terms. This is term 1, and 2, and 3, and 4. Now, how do we go from the term number to the value of the term itself? Well, if you'll notice that these are all squared, right? So we can write these terms as 1 squared, or 2 squared, 3 squared, and 4 squared. So the next term is a to the 5th is 5 squared, or 25. A rule for the nth term is we take whatever n that is and we square it. Alright. Now next, let's number these. 1, 2, 3, 4. A little bit more difficult. How do we go from 1 to 0? Well, I can subtract 1. Does my rule hold up for the next number? If I take 2 and subtract 1, do I get 7? No. So I've got to figure out my rule again. This one is, if I take the term number and cube it, and then minus 1, I have it. Sometimes these are really hard to figure out. So you just have to keep playing with it until you do. So the next term would be 5 cubed minus 1. 5 cubed is 125, so that's 124. And the rule is n cubed minus 1. Okay, checkpoint. Write the first 6 terms of the sequence. So you're going to put n is 1, and then n is 2, and then n is 3, and write out the values for those. Okay, on 2, you're going to number these. So let's go ahead and do that. 1, 2, 3, 4. And then what do I multiply the term number by to get the term itself? Do you see that these are all in the 3 multiplication tables? So there's some plus and minus going on there, so you probably have a negative number. And then think exponents. So see if you can't figure that out. Okay, series and summation notation. When the terms of a sequence are added together, the resulting expression is a series. A series can be finite or infinite. You can use summation notation to write a series. So if I'm going to add up these 4 terms, notice that I put the sigma letter, and then I'm going to put I equals 1. Instead of A here or N, we're going to use I. This means that I'm going to start at 1 and go to the 4th term of the sequence. So that's how I get my 2, 4, 6, 8. because 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and 2 times 4 is 8. And I stop when I get to this number up here. And then I just add them together. Now, what if I have my triple dots here? That means it goes on forever, and it's an infinite series. And I put the infinity sign up there. So, for both series, the index of summation is represented with a lowercase I. And the lower limit of summation is 1. The upper limit of summation is 4 for the finite series, and infinity for the infinite series. So summation notation is also called sigma notation because it uses the uppercase Greek letter sigma written as that symbol. Okay, example 3. Write the series using summation notation. Okay, so again, we need to number these. 1, 2, 3, and onwards. How do I go from 1 to 4? Well, I can add 3. How do I go from 2 to 7? Well, that times I'm adding 5. How do I go from 3 to 10? I'm adding 7. So each time I'm adding the next odd number. Okay, so the first term is 3 times 1 plus 1. So the second term is 3 times 1, or 2, plus 1. So the third term is 3 times 2 plus 3. And the last term is 3 times 15 plus 1. So a to the I, what are we doing to that I every time? We're multiplying it by 3, and then we're adding 1. Now, where I is 1, 2, 3, etc., not to infinity, but to 15, because it stops at 46. So the lower limit of summation is 1, and the upper limit of summation is 15. So the summation notation for the series is 15, I equals 1, 3i plus 1. Now, there's a trick you can do, because I know these are hard to figure out. So here's a trick with things that are adding the same amount every time. You can just think about them as a linear equation with that. I'm going to change colors here. This as your slope. So look here. If I take 1 and 4, the first position is 4, and the second position is 7, and I go ahead and find its slope. 7 minus 4 is 3. 2 minus 1 is 1. And then I put it in the y equals mx plus b. And I stick in my x and y point. 4 equals 3 times 1 plus b. Subtract 3 to get my b. I have this, don't I? So that's a good trick for finding the terms when they add the same amount every time or subtract the same amount. Now, it does get more complicated when they don't add or subtract, like the next one. So let's look at that one. Okay, note that for each term, the denominator is a perfect cube. So, a to the I equals 1 over a cubed. Or not a cubed, I cubed, sorry. So, 1, 2, 3, 4, the lower limit of summation is 1. The top, we have dots after it, so it goes to infinity. And then the summation notation for the series would be sigma I equals 1 to infinity, 1 over I cubed. Okay, checkpoint. 3 is pretty easy. What are you doing every time to I to get the terms of the sequence? You're just multiplying by 7, aren't you? So go ahead and write that summation notation from 1 to this top limit, and then it's 7i. Okay, on 4, that's another easy one too, where you're multiplying the I by every time. Okay, on example 4, we're actually going to find the sum of the series. So this is fairly easy. And they give us the rule, and they tell us the lower limit to the upper limit, and then we just add it. So here's our rule, 2 minus 3k, where k goes from 3 to 5. So I'm going to put in my 3, 4, and 5. Then I'm going to do my math. 2 minus 9 is negative 7. Then I'm going to add 2 minus 12, which is negative 10. Then I'm going to add my 2 minus 15, which is negative 13. So that gives me negative 30. All right, so formulas for special series. There's some specific formulas if you want to add up different things. Like if you just want to add up all the integers, that would be the first one. If you want to add up all the positive numbers, that would be the second one. If you want to add up all the squares, or some of the squares of the positive numbers, that would be the third one. So, let's add up all the sum of 1 through 32. So, that would be n, which n is 32. And we're using this formula here. So then we need to put 32 plus 1 over 2. So that would be 32 times 33 over 2. And if you grab your calculator, that would be 528. So that is all the numbers added together from 1 to 32. Okay, so find the sum of the series. For this one, you just put in 4, 5, 6, 7, and 8 in the math formula and then add it together. On this one, you're going to take this formula and use it to find the sum from 1 to 28, where your n is going to be the 28 number of all the squares.